Welcome to demonstration video 2 in our course ST4 on linear models. Here we're going to look at transforming correlation coefficients. So in the previous section, we looked at creating correlation coefficients, and therefore for a particular sample size, you may have a correlation coefficient of interest. And we defined values for height and weight already. So we're just going to quickly assign weight as being equal to X, and then height as being equal to Y, which we had before, and we can check that they both exist there. So if we look at the correlation of height and weight together, we can assign that to our value of R. And then we have to consider the length of the number of elements there. So we're dealing with 6 elements. That's quite a small sample size. It's not going to be particularly powerful for our analysis. And this formula here that we learned in the slides can tell us more about that. So that's 1 minus, for the denominator, that's 1 minus R squared, the fraction of variation that's not explained. N minus 2 is the inverse of the standard deviation. Then that's the square root of all that, and then multiply that by the correlation coefficient itself. So t-value here will be reasonably high because the R value is high. So you see there 4.32, which you'll know corresponds to the t-value that we had in the car.test function. So we do car.test for height and weight. I see that t-value appearing again, more or less. So we can fit our height and weight together. So we're taking this linear model of height and weight, and then you see the slope there is 0.83, and the intercept is 0.83, and the height is 0.91. We're going to switch that around because we want the intercept of the height to the weight like that. So you can see that we now have the correct model. So it's minus 0.233, and the slope for the weight is 0.9. So we're predicting height based on weight. So now we have the intercept. We can isolate it using the coefficients from the fit function. So we look inside fit, we just type it out and put in $, and you see the different components that we have here, including the residuals, coefficients, effects, rank, fitted values. So they're the fits that we have for our different values, which are the weights. Sorry, they're the heights, should I say? The heights, and then we also have the value for the slope here, coefficients, element 2. Sorry, these are not, this is more accurate. And then the fitted values. So there we have 0.6, 2/3, 5/3, and so on all the way through. So that's a linear increase as a function of the slope that we have. And then we looked at how we can use the standard error of the slope, which we can compute from the fit of the coefficients multiplied by the square root of 1 over the R squared divided by R by the square root of N over 2. So if we calculate that, we can check the standard error of slope B, and note that the slope here is going to be this coefficients 2 value. And we can see there that if we check at the ratio of the slope divided by the standard error, is that it is corresponds approximately to the t value, which is effectively the formula for computing the t coefficient. So that's really what we have here. So we can scale this to estimate the upper bound for the confidence interval limit and the lower bound. So if we do that, we can see the upper bound, and then we can get the lower bound, which is close to 0. So that indicates quite a wide confidence interval. This may be because we have very few samples, but also reflects the heterogeneity of the samples themselves. If we had a larger sample size, then perhaps it might reduce somewhat. Also, we can look at how we convert go from the correlation coefficient to Cohen's d value, called ds here. And with the formula for that, we have to consider the sample sizes of each of our groups, n and m. So they're assigned the values of 14 and 16. We have the total sample size n, and our d value is starting at 0.1. we don't need that initially at the start, but then we do need an empty vector set correlations into which we store our d values, our corresponding correlation values when we compute them. So in line 82, what this is doing, it is computing a value for based on d. So d is equal to 0.1 here. So it's scaled by the total sample size and the sample sizes of each of these groups. And it's looking at how the Cohen's d is scaled based on that. So we're submitting values of d to calculate r. So if we look at what r is in that case for a d value of 0.1, we see that value is 0.05. If we change d to be 0.5, so it's much larger, and look at what we get, we see now the correlation coefficient is much larger. If we change to be something that's really, really big, 2.5, we'll then see that the correlation value is very, very high. So what we can do in this for loop is count the values going from 0.01 to 1 in increments of 0.01, because that graphically will look nice. And we're submitting these values of d to this function r. We're storing these values in the set correlations r vector, and then we're going to plot them. So we're plotting these values against set correlations, and that's currently empty. So if we run this loop, we'll then find that we have lots of values in set correlations. We can see it there, and then we can plot them and add a grid and other things if we wish to do so. So if we see this, what we're looking at here is the x-axis indicates the d values that we're looking at, and then the y-axis is the correlation coefficient that corresponds to those d values. We can even look at how we get the r squared value. So we'd have to look at r squared here instead. We reset the vector to be 0, and this plot now would indicate the r squared value on the y-axis, which you can see has changed somewhat, and then we have the d values still on the x-axis. So that's a good way of scaling the effect size and the correlation coefficient. We can expand this as well to a value of 2 to see what we get. If we do this after resetting the initial vector, of course, first, we have to increase our number of values. There, we can see we get a wide range of correlation coefficients, and we could increase this further, say to 5, and do the same for the plot to see if we get much higher correlation coefficients. So let's just try that once more, and then if we see for that plot there, we get higher correlation coefficient values. So what you can do is try to add your own annotations for X and Y lab on this plot, and try using different values of sample sizes to see ones that are more relevant for your work. And then using question 3, using your own model for question 1, 2, write code to get the corresponding t value and a 95% confidence interval for that slope as well.